Hi, this is Kevin, and you're watching Google Engineer Explains. Today we're going to talk about LeetCode problem number 9, palindrome number. All right, for this question, basically the idea is you're given some number x, and the number it needs to be. We're going to find out if the number is a palindrome, which means it's basically the same forwards or backwards, right? So some examples would be like 121. If you take 121 and flip it around to backwards, it's 121, so it's still the same, so that is true. If you take a number like 10 and you flip it backwards, it's 0, 1, and that is not the same as 10, so that's false. And here we have negative 121. Negative 121 flipped backwards is 121 with a dash at the end, which is going to be false as well. And actually from this you can see that basically all negative numbers cannot be palindromes, right? Because you can't have a number with a dash at the end of it. So anything with a dash at the front is going to be not a palindrome. That's going to become important in a second. All right, so I think from this we kind of understand the problem. It's not too complicated. So how would we come up with a solution? Well, I think that's pretty straightforward. We've already kind of shown it, right? Like create this copy, this backwards copy, compare it with the initial number, and if they're the same, then you have a palindrome. So create a backwards copy of the number. If backwards copy is the same, return true. Otherwise, return false. All right. So I think that's like probably the easiest way to understand this. So I think we should go ahead and try to figure out how we can implement something like this. All right. So I think the next challenge becomes like, how do we create a backwards copy of the number? And I think like one way you could do this is actually by taking your number and making it into a string, and then doing string, dot reversed, which are just native Python solutions, and then kind of comparing the string with a string version of the initial number. Yes, that is correct. It will probably pass the LeetCode checker here, but I don't think that's really what the interviewer would be looking for, because you wouldn't really be demonstrating any algorithmic complexity. So let's try to do it like a numerical way. All right, so let's take a number 1, 2, 3, 4, for example, and we want to basically, so let's do it like this. Let's call this our copy number. We'll take a copy of our initial number, and we're going to make it into we're going to slowly build up B, our backwards version of the number. So what can we do? So let's say we have 1, 2, 3, 4, modded by 10. The mod thing, basically, it just takes this initial number, divides it by 10, and then tells you what your remainder is. So it's 4. So basically, if you mod by 10, you're just going to get whatever's in the ones digit. And that's the case for all positive numbers. Okay. Let's say, now, all right, so we have 4 here, right? And then what we can also do is 123.4 divided by 10. In Python 2, we have integer division, so it just rounds down. It's actually 123.4, right? But it just rounds down to 123. So we can say, our C starts at 122.34, but we can actually update it to be 123, and B, we can give it the 4, right? So we got the 4 from here, and the C gets updated. So what do we end up with? We basically have taken one digit off the end of the C and put it onto the B, right? The C has removed the 4 and put it on the B. Let's just do one more iteration to show how this would look as we continue further on. So 123 mod 10, oops, we get 3. And 123 divided by 10, we get 12.3, right, which is 12 when using integer division in Python 2. So C becomes 12, and B becomes, all right, so B is 4 right now, right? So what we can do is take b, multiply by 10, so 4 times 10 plus 3, you get 43. And that's the same case here, right? If we started with b of 0, then it would be 0 times 10 plus 4, and we end up with 4 for the first one. So now b is 43 and c is 12. And so you can just see like you're basically slowly building up this backwards copy, right? You took the 4 and the 3 and you moved them over to the b, and then the 12 has the 1 and 2. So if you were just to continue on this until c was 0, you would end up with b is equal to 4, 3, 2, 1, right? And that's basically your backwards copy of the number. So all we have to do now is create this backwards copy of the number, compare it with our initial x, and see if they're the same, then we know that we have a palindrome. All right, so let's go ahead and try doing this implementation. So basically, we're going to take a copy, right, which is equal to our x. We're going to have v is equal to 0, right? These are our initial values right here. And then we say while c is not 0, or we can just say while c, then backwards becomes c mod 10, backwards times 10 plus c mod 10, right? That's just this right here. Your b value times 10 plus your c value modded by 10. And then c becomes c divided by 10. Or you can also say divide. C is equal to the c divided by 10. Okay? And then you'll just repeat this until the c is 0. So then your b, your backwards, will basically be a reversed version of x. So then you can just pretty easily say return does b equal x, right? So in the case right here, you have 1, 2, 3, 4, and then b would end up as 4, 3, 2, 1. And so those are not equal, so that would be false. But if you had something like 1, 2, 1, then your backwards would be 1, 2, 1, so then those are equal until you be true. We also mentioned earlier that all negative numbers, it's impossible for it to be a palindrome because there cannot be a negative symbol at the end of your number. So, basically when you reverse it, this is not a real valid number, right? So we already know that negative numbers cannot work. So we can actually exit out early if we have a negative number. And that's helpful because this mod stuff actually doesn't really work that well with negative numbers in Python 2. So let's actually just get out of there. Just forget about that. Like if we just get out whenever we see a negative number, we don't even have to worry about it. So if we have a negative number, if x is less than 0, then we're only going to do this operation with positive numbers. So then we can assume that everything works correctly. All right, so let's go ahead and just try running this. Make sure that this works. So all right, it works just for like this really basic use case, 121. I'll go ahead and submit this. Nice. All right, cool. It worked. Okay. Let's see here. So we covered, let's talk about test cases. Test cases, talked about negative numbers, right? Are always going to return false, and we already captured that here. What about, so we talked about positive, this should work for all positive numbers. What about 0? All right, so let's say we have 0. Well, b will equal 0, c is going to equal 0 here, while c is equal to 0, so it's going to break out right away, or while c is a positive number. So then does b, the backwards, equal x? Yes, it does, because they're both 0, so this actually is also true, so we catch that use case. One other interesting use case we might run into is, like, let's say we have a number that has 0 at the end. So why is this interesting? Basically because, like, let's say it's 1, 2, 3, 0. Your backwards, the first iteration actually stays as 0. So it actually ends up being 321, right? It actually, well, it becomes 0, 3, 2, 1, but the 0 is dropped, so it becomes 321. So this is false, but let's say we had something like 121 here, right? It almost looks like we might get into a palindrome because our backwards ends up as 121. It's off by 1 digit, but the 0 would end up in front, right? But it's pretty close. So one thing we can also note, we might need this later, is that anytime a 0 is at the end of your number, it can never be a palindrome because the 0 gets put to the front, and you can't have a number with the 0 at the front like it's not a real number. So it might just be something to note later. Cool. Anyways, going through the test cases, it seems like this is working, so I think we're good. Let's talk about time complexity, time and space. Oops, just put it in. All right, so time is O of n. Why is time O of n? We basically do this iteration once for each digit in C, right? And C becomes less by the 1 digit each time. It's divided by 10 each time. So time is O of n, where n is the number of digits in X. This is important because in the solutions they give, they actually say it's log. I'm going to use a different variable here, log k. This k and n doesn't matter. I'm just using this to differentiate that they're two different things. So why is it log k? Well, that's because if you have to do this once for each digit, that's the same as saying like if you log k, that's how many, that's the number of iterations you would do. So basically where k is the size of the number, right? So like the reason, right, like log 1000 base 10 is 3. Log 100 base 10 is 2, right? So basically the log k is just also, it's the number of digits. So if you use k as the actual size of the number, then log k is the number of digits. So this is really saying the same thing. So it's basically O of n, where n is the number of digits, or log O of log k, where k is the size of the number. I know it's might be hard to grasp this, so if you need to pause, feel free. All right, space complexity is, all right, so basically we don't have any external data structures or anything. We're just storing everything in these two variables, C and B, and they're just both going to be integers. So technically we can say this is constant space because we just use two integers regardless of the size of the number. Cool, so I think this solution basically works, and in my opinion, this is the easiest solution to understand and implement. In an interview, I think it's a good solution to use because it's very straightforward, and it's easy for you to understand, so it's less likely you're going to make a mistake when you do the implementation. Basically, just take a number, reverse it, and compare it with the original number. All right, so I'm going to just, another solution they give you is this one right here. They revert half of the number. So this is different from the way I described it. And I'll explain this one as well, just so that people can have an idea of what this is. But basically for this one, I'll make some more space here. So this solution, in my opinion, I think is a little bit more efficient than the solution I just implemented. Although it's a little bit harder to understand in terms of the corner cases. So there's more places where you can make a mistake. Let me comment this out too. All right, so this is going to be solution 2. All right, so basically for this one, the idea is, let's say you had a number 12321. You would basically, what you can do is, instead of reversing it, let's use another number actually, 1234. Instead of reversing it fully, you can actually just reverse it halfway. So you would end up with 43 and 12, right? So basically you take these last two and reverse it, and then the front two. And if they're the same, then that's a palindrome. So for example, let's say you had 1221. If you reverse the back two, you get, if you reverse this part, you get 12, and your initial number is 12. So you can see, right? It's basically comparing the left and the right halves, which makes sense. And if let's say you had an odd number of digits, if you to reverse it, it would look like this, right? 21, or the 3 could be on this side too. Or it could be like this. Oh, I did this backwards, sorry. 1, 2, 3 if you reverse this side, right? But the point is, like, whatever one is bigger, just drop it, the last digit, and then compare, and then you also have the same. You can see that it's a palindrome. And if they're not the same, then it's not a palindrome. All right, so basically we can come up with the our algorithm, right? Reverse half of the number, compare it with our original number. Pretty simple. All right, so let's for this, let's go ahead and try to do the implementation for this. Okay, so we're gonna create backwards. This time we don't need to create a copy. We can just use our initial number because we're only comparing against the, you'll see. All right, so while x, all right, so when do we stop? Okay, I'm just gonna, while something, we're gonna say our backwards is gonna be equal to backwards times 10 plus x mod 10. So this is very similar, right? We're just taking one digit off the end, like I described in part 1, and adding it to our backwards copy. And then our x is going to be divided by 10. So this way we're just taking one digit off the end of x. So let's say we had 1, 2, 3, 4, right? Then b becomes 4, x becomes 123, right, in this part. All right, so when do we stop our iteration? So in the first type of algorithm, we stopped when our original became 0, right? We just reversed the whole thing. But in this case, we only want to reverse half. So it starts off like x is always going to be bigger than b, and then at some point, b might be equal to x. So it starts out x is always going to be greater than b, so we should stop when x is less than b. Right? Just makes sense. Like b has slowly become big enough than x. Or does that make sense? So, all right, so it'll basically be like this, right? So while x is greater than b, we'll keep iterating. As soon as b becomes bigger than x, we stop, right? So when b is bigger, this is no longer true and we break out. All right, what about this? Like, do we need this equal, right? Is it greater than or equal, or just greater than? And I think this is important. Let's say we have a number that is 1, 2, 2, 1. B will become 1, 2, and x will be 1, 2 at some point. And we actually need to compare at this point, right? So when they're equal, we should actually break out. So it starts out x is bigger. As soon as b becomes equal, we should also break out. So if b becomes bigger or equal, we'll break out. So we would actually not keep this equal sign, right? This is saying like we'll continue if x is bigger, but as soon as b becomes equals, we break out. So we keep out the equal sign. All right, so then from there we say return x equals b. Is that enough? So in this case, so let's do some use cases now, right? Because this is why I don't like this algorithm as much. It's a little bit more confusing and complicated. Let's delete some of this stuff. So let's get a couple use cases in here. All right, so let's go with the few even cases. All right. So how's this going to break out, right? All right. X and b. So as long as once x is less than b or equal to b, it'll stop. So x will become 1, 2, b will become 2, 1. Or sorry, 1, 2. It gets reversed, right? And now b is the same as x, so it breaks out of the loop. And then from there, we get true because x is equal to b. Okay, what about this one? We get x is 1, 2, b becomes 1, 3, right? B is greater, so we break out, and this returns false. So that's fine. For this one, you get 1, 2 for 1, 3 for x, this part, and b becomes 1, 2. Oh wait, b is still smaller than x, so actually this 3 moves over, so it becomes like this. And are they not equal? So this is fine. So this is also returns false. So I think for all the even cases, we're good. What about the odd cases? That's if it's like this, right? Or a false case. Odd number of digits. So x would end up being 1, 2, and b will end up being 3, 2, 1. How does this work? Well, b, so this middle digit is always going to end up on the b side. Why? Because, oops, it is backwards. Because when it's like this in the previous iteration, it's one more digit, so it's always going to be bigger. So it'll have to go through one more time until x is less than, right? So it'll go like that. And for this one, it'll be 1, 2, and 2, 2, 3. Is that right? 1, 2. Yeah, because before that it'll be 1, 2, 3, and 2, 2, which x is bigger, so then the 3 will move over to here. So this one, so with this, now x and b are not equal, and it's impossible actually. For the odd case, they're never going to be equal. So this is not going to really be enough to cover it. So we want this to return true. How do we get this to return true? We can say x equals b divided by 10. Why does that work? So if we divide b by 10, so let's add one more column, b over 10, then this becomes 12, this becomes 22, right? And we can compare 12 with 12, so then it works. 12, 22 does not work. So if we do b over 10, basically we're just dropping that last digit, that middle digit, right? This 3. We don't care about the middle digit in the odd case anyways, so that's fine. All right, so if we add this in here, then we get true here, we get false for this case. But we have an or statement, so we also have to make sure that when we go through the odd case, we want it to go through here, and for the even case, we want it to go through here. So one way is like just make sure for the odd case that this one is always false, so that it always has to be whatever this one is. So is that the case? Well, actually, if you look at it closely, it is, because with the odd case, one side will always have more digits than the other side. So this will always be false in the odd case. So it's just going to be whatever this is. And this is basically comparing, right, the correct thing. So this is fine for the odd case. And then for the even case is a little weird because like it's possible the numbers could split exactly evenly, or the x could have 1 or 2 less digits than the b. So for the even case, we're only looking at this comparison is what we care about. If it doesn't split evenly, then it's false anyways, because that just means that the numbers didn't really work out, or they're not a palindrome. So we only care about this. So we want to make sure this is always false for the even case. And is that the case? Well, if they're the same number of digits, then if you divide b by 10, then b will have 1 less digit, so this will always be false. So that's fine. And if b has 2 extra digits and you divide b by 10, it'll have 1 extra digit more than x. So again, this will always be false. So for the even case, the only way that I can return true is in this case. So having this return statement like this basically catches the use cases. So I think we're fine there. Cool, so this basically does it. But then, okay, so we also forgot to say, right, if x is less than 0, right, just the stuff from earlier, return false. Right, negative numbers, we don't want to deal with them. And then also, there's also another use case we talked about earlier where, let's say we had a number with a 0 at the end. This can never be a palindrome, right? But it actually, let's do like this, 1, 2, 1, 0, right? This is not a palindrome because if you put it backwards, it's not the same. And it can never be any number with a 0 at the end cannot be a palindrome. But if we put it through our thing right here, b actually becomes 12 and x becomes 1, right? Because b actually, it actually becomes 0, 1, 2. But the 0 cannot be at the front of the number, it doesn't actually do anything. So it ends up being 12, and then we go through this bottom comparison, right? It's basically just the same as like, is 121 a palindrome, which it is. And so we'd actually get a true result, but it's actually wrong. So we can actually just check, like, we just have to just make sure to say if x mod 10, meaning the last digit of x, if that's equal to 0, then return false, right? All right. What if, so that takes care of the case if the end is a 0. But what if we have 0? Well, we don't want this to return false, so we should say and x does not equal 0. All right, so that's basically it. So we have these two cases that so basically when we get down to this point and do the iteration, we only have numbers that are non-zero, do not have a 0 at the end, and are and are positive. So then this will catch all the rest of the use cases. All right, so we can basically just take this and combine it with the part above here, or that, and that should be it. And this is basically the solution they give you in the solution here. Let's just make sure this works. Okay, cool. This also worked. All right, so what's the runtime complexity of this guy? It's actually the same. Time, space. It's big O of n, where n, whoops, n is the number of digits. Right, we're only going through this iteration once per digit. And space is constant space because we're only storing this extra one integer. So we're not having any other data structures. Okay, one thing to note here, this is more efficient slightly than the other one in terms of time complexity. It's still O of n, but you only have to do an iteration for half the number of digits. So you do half the number of operations, so it's actually a little bit more efficient. But the time complexity is still the same. It's still in the order of, we drop the constants in the time complexity calculation, so it would basically be like, 1/2 n, right, 0.5 n. We drop the constant, so it's still big O of n, but it is an optimization over the previous one, although it is slightly more complex with this here, right, and this extra use case. But yeah, that's how you would solve this, another way of solving this. Cool, so hope this was helpful, and hopefully you understand this a little bit better. If there's any questions or topics you want me to cover, feel free to post those in the comments, and I will see about making a video for them. Or if there's any other LeetCode questions specifically, happy to cover those as well. Thanks so much, and best of luck with interviews.